So we're talking about deriving the charging function. And I think it makes perfect sense to take a look at the charging and the discharging equation because they're so similar and they're done almost the exact same way. And I'm pretty sure we can probably move through it relatively quickly. But remember, for this to be effective, you have to be able to do it. So we're going to see how good your memory is in this. We'll do a straightforward single EMF. Although we probably, maybe Monday, we'll take a look at circuits with multiple EMFs in them because that seems to be something that throws you guys too. You know, we have two batteries and they're not necessarily cooperating. All right, so switch, resistor, capacitor, and our EMF. So you know that if this is an FRQ, there's going to be a whole bunch of text and prose establishing the circuit and probably establishing some variables that you're allowed to use in your argument. So one of the things they're probably going to do is talk about the fact that the capacitor is uncharged, there's no electric field between the plates. They may even go so far as to describe if there's a dielectric being used or not. You understand that it's about word count. They're going to be trying to get the word count up as much as they possibly can. But the mistakes that you guys tend to make is not using the letters they use in their argument. Use their letters, whatever it is. So if they have an EMF symbol, use the EMF symbol. If they have a V for voltage, use the V. So you need to be mindful of that. If you change out a symbol, you can lose all the points that involve that symbol. So they're also going to spend a lot of time establishing things like making sure there's no alternate ways that you could interpret the question. That's part of the establishment of adding all these extra words is to rule out any ambiguity so everybody's doing the same question and they're doing it hopefully with the same intention. So most of the extra prose isn't just there to drive up the word count. It's because they didn't do it in the past. People found that the questions were ambiguous, did the questions multiple different ways or interpreted it different, and they had to relax their scoring guidelines. They don't want to do that anymore. So that's why the word count goes up. So in this circuit, the first thing you should do is establish that, the charge on the capacitor is 0 at time equals 0. I'm inventing a symbol, Q, to describe the charge on the capacitor at time 0. And there would probably be a paragraph describing that. So here's your job. Time 0 is when the switch is closed. The first thing that they should ask of you is to create but do not solve a differential equation that could be used to find the charge across the capacitor as a function of time. All right, so you needed to start with a first principle, and it looks like almost everybody chose the right place to go. Would anybody like to tell me what their starting equation was and what the name of the principle is? Anthony? Excellent. So you use Kirchhoff's first law to start your equation. Any question? That's a good place to go. You're unlikely to have to name it, but they are looking for you to do something that's going to sum up all the voltage drops in the circuit and set it equal to 0. That's our first principle. We want to create a differential equation, though. So this isn't a differential equation. How do we create this? How do we create a differential equation from here? Go ahead.
Replace the time with dq.
Here we go. So everything we've just done probably is worth a point, even though it's relatively minor. And if we're looking at 15 points across standard FRQs, 2 points. And that's a good start, but that's probably it. They're probably going to have a question B that says, now that you have a differential equation, show using integral calculus the solution to this differential equation. So that's where the real work begins, and we have a process that we've been using for that, which is to separate our differential and then integrate both sides. So can you get it all the way to the point where you're about to integrate? probably still only worth 1 point. But can you get it all the way to the point where you're about to integrate? All right, so a few of you are stalled, and that's okay. Step 1, isolate the differential. You got to get this by itself. You don't have to get it all the way by itself. You want it on one side of the relationship. So it's the only term on that side of the relationship. Now, you can divide out by r if you really feel like it, but you don't have to. You can leave it right there. It's just a constant. The constants don't really get in the, they just get in the way. But you have to separate the differential now, which means multiplying both the top or both sides of the equation by dt. Now you have to collect terms. And this is where we get into a little bit of trouble with some of you from what I just saw when I walked around. Collecting terms means to get anything that has the functional variable q on the same side as dq, and anything that has the functional variable t on the same side as dt. Now there is no t in this equation, but there is certainly a q, and that has to be moved over, but you can't just like take the q out and move just it over. Because the entire thing is being multiplied by dt, you have to divide both sides of the equation by that entire function. Now you're in a position to actually do your integration. And again, here you can take some liberties. You guys who are in integral calculus note that you can do this as an indefinite integral and apply your limits later. I'm still suggesting to all of you who understand that statement, I'm gonna tell you, please put your limits on here. That's what they're looking for on the AP Physics exam. You can do it both ways, it's mathematically the same, but you're gonna score a point for proper limits. And we have limits. One of the ones that's important here is to note that at time 0, the charge in the capacitor was 0. And the upper limits aren't real limits. There are functional variables because we're trying to create a function out of this. So the top has to be the functional variable for t, and the top of this one has to be the functional variable for q. Now, I had to sit and explain a little bit in my mechanics class that writing something as a function, like q is a function of t, this is not q times t. I didn't realize I had some students in mechanics that thought when we were doing a similar thing for velocity, that when I wrote this, they're like, well, why are you multiplying by t? I'm not. But I will often write this as the functional variable on top, as a reminder that it's not some specific value for q, it's q sometime in the future. So these upper bounds are just functional variables, but that's not q times t. That's q as a function of t. All right, probably getting to here, 1 point. And then doing your integral calculus and all the associated algebra, another point. Now, it is quite possible they will give you the answer. They will say, show through integral calculus that this is the answer. If that's there on the exam, I'm not sure it's worth doing the algebra. Just write down the answer now because this leads directly to that answer. And the algebra is going to cost you minutes. Now they're giving you the minutes this year. You don't have to do all the FRQs in 45 minutes like before. You're going to have 100 minutes to do your FRQs. So you've got time. But I'm not sure it's well spent on the algebra still. We're going to do the algebra though. So calculus first though. I'm not going to bother with the left side very much. We're all good there. But it's the right side that we have to do something. What's the calculus principle you guys use here? This is a U sub. So has it ever occurred to you guys that it doesn't have to be the letter U for U sub, that you can make up any letter? Okay. Do you guys still just use U because that's how you learned it? Going on 40 years since I learned it, and I still just use U, so I don't know why. What do we do after we make our substitution? What's the next step in doing U sub? With respect to? All right. What do I do next? Solve for dq. Now we're in a position to do substitution. I know that I don't do it this way, and I'm sorry if it bothers you. In calculus, you're supposed to also go and put your limits in and get new limits. I never learned to do it that way, and so it's not my habit. If it makes you feel better, we could try it that way so you see it the way you're supposed to. No? Okay, good. So I just kind of casually throw everything in here. And there, all the pieces there. Pull out that, and then integral of 1 over u with respect to u. And finally, we all good with just going ahead and putting in the original function again? All right, so we've done our calculus. We have to put in our limits to finish this off. And we put in our limits, we get messy. All right, so now it's just algebra. But not just any algebra, right? Lots of algebra. Now, I always kind of blow through the algebra thinking that you guys are good at this. Is that wrong? Are you okay kind of blowing through the algebra step by step here? Do we need to stop and take stock of it? Or do you want to just run through it yourself? I tend to think the algebra is the least interesting part here. All good? Just so laborious. Now, I think that you'll probably want to do this. Factor out that common term so we get that 1 minus the exponential inside the parentheses because it gives us our asymptotic look, and it also kind of tells us what we are asymptotically reaching. Should we leave it like this, or should we express it a different way? Go ahead. Yeah, I think we should replace it and put in Q max. But you'll have to answer that question based on your problem. So if your problem had just the exponential and C, you have to leave it like this. But if they define something that indicates an understanding, then yeah, you can make that substitution. What's important for you to know is that it's quite reasonable for them to have you stop here. And that's great. And then ask what is the meaning of, the E times C. That's great, but this is where we end. And this is an asymptotic relationship, correct? So you understand what I mean by that? So it's going to approach some asymptote, and that asymptote is going to be whatever this value is. That's kind of our expectation. Can you do two things now? Can you put together the voltage as a function of the time, and can you do the current as a function of the time? Let's say the voltage over the capacitor and then the current through the resistor. Can you do those? So Yeah, the voltage, we're just using the definition, that you take charge and divide by capacitance to get voltage. So V as a function of T is just this. Now this would not be the voltage across the resistor. This is the voltage across the capacitor, which grows at the same rate that the charge grows. But you had to take the derivative to get the current. It's not terrible, right? Go ahead and distribute. The first term's a constant, so it just goes away. And that leaves us with taking right? First term goes away. What's that? Okay, not minding. Chain rule. C's cancel. All good? We just got Ohm's law again, don't we? This would be I max. Again, we may not replace that. We might keep it in the terms that they gave us. But this would represent the current at the very start, showing how we have maximum current at time 0 and the current tapers off. And just in order to be thorough, if we wanted voltage across the resistor as a function of time, it would come from Ohm's law again. So we would just take R and multiply by our function for the current. That'd be it. The R's will cancel. This is what paints that picture that we're supposed to know, that at time 0 in a circuit that has no charge on the capacitor, it acts as though it's got 0 resistance, and we get full voltage across our resistor. And over time, as the capacitor charges up, it looks like it has infinite resistance, and we get no current passing through any leg of the circuit that has a capacitor. This is where we got that information from. So that's a lot. I don't think they're going to ask you to do this, but being able to do that, starting with your charging function and producing voltage, current, and voltage across the resistor, not an unreasonable expectation. Pretty straightforward. So there's 9 minutes left. Bring back the original circuit. So switch 1 has been closed for a very long time and is then opened. A new time 0 is established when switch 2 is closed. Can you derive a function that would describe the current through resistor 2 as a function of time? So end stage question, but you still have to do a differential equation to get to it. So can you derive the charging function or the discharging function for a capacitor where time 0 now is reset for when switch 2 closes? Just repeating the same question, but for a fully charged capacitor. And just to make it a little bit straightforward, the capacitor would have would have a voltage of the EMF of the battery after it's reached a steady state condition. So the question is, where do you begin on a discharge circuit or discharge function? What's your differential equation and what's your solution to your differential equation? This one's easier. You should be able to do this one pretty easily. Yeah. Say it again. Switch 1 has been closed for a long time and then is opened, and now switch 2 is closed. So I'm just gonna kind of silently go through, since most of you are now redoing a step. So does that get you guys caught up to just right there where we're doing the limits? Does that look okay for you guys? Could be minor differences in the way you did your algebra. But it is appropriate to establish that our capacitor is charged at time 0. If you put Q max there, you'll still have to replace it at the end to be in the same kind of symbols that we've been using from the beginning. All good? The rest is just algebra. But again, I say it like that, but there's still a lot of algebra there. So all you gotta do now is combine those like so. Raise everything to base E. And multiply both sides by EC. That gives you your discharging function.